Start recording. All right, we got a review for the test. We're going to start our test tomorrow. Find the area of the enclosed region. I thought, well, let's review, working with y instead of x. So x is equal to negative y squared, and x is equal to 2 minus 3 y squared. We're finding the area, not the volume, so we want to know normally which is the top function, which is the bottom, but here we're going to look for which is the right and which is the left. Negative y squared would look like this. And then if I plug 0 into the other one for y, we get 2. But then this is going to the left much quicker than this one, so it looks more like that right there. We want to find the enclosed area. There we go. We're going to find that area right there. So we need the intersection points. So negative y squared is equal to 2 minus 3y squared. Add the 3 over. Y squared equals 1, so y equals plus or minus 1. So we're down to negative 1 up to 1. So that means you have a couple ways to do this, and I don't think we're going to do any integration today. You go negative 1 to 1, or you could go 0 to 1 and double it because we got symmetry over that x-axis. I prefer the bottom one because I don't like keeping track of negatives. But I got to make sure I'm 100% sure that there's actual symmetry going on, and there is with this case. All right, now instead of top minus bottom, I want the right minus the left. So this is the right function, that's the left function. So now we just have 2 minus 3y squared minus negative y squared, or plus y squared if you will, dy. And it's the same thing down here. So you could write plus y squared. That'd be the exact same thing, of course. You'd combine the like terms, integrate, and solve, and evaluate. On the next one, I have 5 parts to this one graph. So if you want to keep drawing, you should probably draw very lightly, and then we'll keep erasing, because if we try to do all 5 on one, it's going to get really messy really quick. So A, set up but do not evaluate. A, the volume of the object whose base is R and the cross sections perpendicular to the x-axis are semicircles with diameters in the xy plane. So I'm not going to draw on that one. I'm going to draw over here. There it is laid down. So we have this plane that's sitting like this, and we're going to lay that down. And now coming off of the paper are these semicircles. So we have this 3-dimensional object that we're going to try to find the volume of. So the semicircles are sitting here. The diameters are perpendicular to the x-axis, and here's one semicircle sitting right there, coming off of the paper. Now we have a whole bunch of them. We have, a little one over here, and as they go to the center, they get bigger and bigger. The whole concept is adding up an infinite amount of those circles, and when you add up a bunch of areas, you get volume. So we're going to add up all of them from 1 to 3, and I know that probably copied really tiny for you, but it says 1 to 3. 1 here, 3 here. The cross-sectional area is a half of a circle, so 1/2 pi r squared. Just half circles, not full circles. Semicircles. All right, anyway, the diameters are sitting on the xy plane right here. So we have 1/2 pi, and the radius is going to be this function. Here's the diameter, so that'd be the function value, and then divide that by 2. So negative x squared plus 4x minus 3 divided by 2 squared. There's the radius squared. Any questions on that one? B. Where should I put B? How about right here? B, the volume of the solid if R is rotated about the x-axis. Now we're going to take this and we're going to rotate it over the x-axis. So we're going to rotate like that. The cross section is area we're going to integrate from 1 to 3 of pi times r squared dx. And now the radius is going from the x-axis up to the function value. So now the function is the radius. We don't have to cut that in two. I want to erase that so I have room. Everybody good? Anyone still writing? All right. So that's what we do. We did B. I guess I'm going to erase all of this. I can undo if you need to see it. I can undo. Everybody good? All right. C. The volume of the solid if R is rotated around the y-axis. Let's erase this. Oh, I guess the parabola about the y-axis. So that's probably over here somewhere. It's kind of going off the screen. Rotate this all the way around. Rotate this all the way around. So there's the other edge, roughly, of the cylinder. Now, I had a couple students come in today and ask whether, how do you know when to integrate with respect to x and when to integrate with respect to y? So what should I put at the end here, dx or dy? What do you think? Dx, right. Because we're picking the edges of the cylinders by picking the x value. So the heights of the cylinder are being selected by whatever x value we pick. And so we're picking a bunch of x values along here, a whole bunch of them, right? All decimal values. So this is actually dx. Now we need 2 pi RH. So let's identify the endpoints of our radius. So the radius, well, we're rotating this around the y-axis, so here's one of them, and then here's the other endpoint for this one cylinder. So there's the radius. And you can always subtract if you want. Here's the x value that we chose, minus, that's actually 0. So you can put x minus 0, no problem. I mean, you don't really need to. You can just put x. But if you want a hard and fast rule, identify your endpoints of your radius and take the right minus left or the top minus bottom, and it'll be right every time. Now, I wouldn't put x minus 0. I just put x. And then the height is the function value when you pick your x. So negative x squared plus 4x minus 3. Don't need the minus 0, but I certainly wouldn't count it wrong. You need the x. All right, letter D. The volume of the solid if R is rotated round the line x equals 4. Everybody good here? I'm going to erase the diagram because it's going to get really messy. All right. Where x equals 4. So 3, 4 is right here. The halfway around would look something like that, I suppose. If we pick this x right here, that would rotate over here, like that. And there would be one shell. And we would add up an infinite amount of those shells. We would get the solid. So 2 pi. I still need to go from 1 to 3 on this last one, by the way. 1 to 3. This one is also 1 to 3. We need the r and we need the height, dx. So 2 pi RH. The radius is, let's identify the endpoints. Here's where it starts, and this is what we're rotating around right there. There's the radius. Now that's 4, and that's that arbitrary x value. So right minus left. So 4 minus x. And then the height on this one, again, is the function value. Negative x squared plus 4x minus 3. There's the height. And then what if we rotate it around all the way over here to x to negative 2? Let's say that's negative 2. And then here's our x value, and it would go way over there, and it'd come back this way. So it's kind of going off the screen here. Coming back like this. Oop, that was weird. There we go. So letter E, 2 pi. We're picking our x values from 1 to 3, all of those cylinders. So integrate from 1 to 3 of r times h dx. So the radius goes from this x value that we picked all the way over here to -2. There's the center of the cylinder because that's what we're rotating it around. So this right here, from the x to -2. So x minus -2 or x plus 2, and then negative x squared plus 4x minus, I think that says -3. So there's shell method for that. Now the reason we can't use washers is because it's the same, they're not two different functions. I can't do this and this with the same function. Can't do that. I mean, maybe we could get it to work, but I'd rather not try to get it to work. I'll just use shell. How about washer? Let's find the volume of the solid when r is rotated around the x and the y axis. So square root of x and x. Let's go around the x axis first. Here and here, that'd be halfway around. Pick some arbitrary x value. We're going to rotate this around. So this first one, I'm going to integrate pi times big R squared minus little r squared. And both of them, we're going 0 to 1 on the x and y. But now, if the washers are like this, should it be dx or dy? Oh, I heard dy, and I heard dx. We sure dx? Sure dy? We have to get the radius. And when we pick this x value right here, to get the radius, we will plug the x value. Well, let's not only pick x, let's pick a value for it, which we usually don't do. But this is 0.5. Let's say this is 0.49 or 48 or whatever. To get the height, to get the length of the radius, you'd take 0.49 and you'd plug it into each of these, and you would get the y value, and that would be your radius for each. So we got to plug, if we're going to plug x values into something, our formulas better be in x, right? So this would be dx. Minus, we're minusing these two. I need a minus in between. So this is an arbitrary x value. To get the long radius, we would plug into the square root. And to get the inside, the short radius here, the small radius, we would plug that into the line, which is x. There we go. Now if we take that same thing and we rotate it around the y-axis, it looks something like that. Rotate, rotate. Now we're picking a y value to get this length. We're picking a y value to get that length right there. So now this one's going to be dy. So this one was x equals 0 to x equals 1. This integral is y equals 0 to y equals 1 dy. But now I need these to say x equals. That'll be x equals y squared, and that just says x equals y. The outside circle goes to the line. That's going to be y squared. I don't usually write it like that. Y squared minus, and then the short one now is going to the curve, the parabola, which is y squared rather than square root of x. Y squared squared. So when you do your homework, you got to make sure you know whether you're integrating with respect to x or with respect to y, and that'll be a big deal on the test. You know, that'll lose you some points. All right, you want to try this one? Just rotate around the x-axis. Just set it up. Oh, yeah. Yeah, sure.
Why is it this equation minus this one?
Did I do it backwards maybe? Let me look. I'm gonna go up to the board here and I'll go back. So the outside radius goes to the line, right? This is the line.
Oh, okay. Big minus. Yeah.
And I'm squaring y. Good now? Okay. You had me worried for a second. All right, let's keep it. Oh, this says 2, 4, and 6. I can barely read it up there. You probably can't even read it on your paper. So we're going from 2 to 6, by the way. It copied really tiny. We're rotating around the x-axis, so the line is the inside, and the curve is the outside. So we're integrating from 2 to 6, which you probably couldn't read, pi, and then the inside radius is going to the line, and the outside radius is going to the curve. It'd be fun to square that, so let's not. Did I do that right? Oh, do I have it backwards? Oh, I have it backwards. I have it completely backwards. That's right. Yep. Yeah. 2 to 6. It's the curve. I just went first and second. I need big minus little. Yeah, that's completely backwards. Squared minus 6 squared. Thank you. Yep. A particle moves along in a straight line with velocity x squared minus 9. If s of 0 equals 6, find the total distance the particle travels between 0 and 5. So this s of 0 equals 6 is a total distraction. You don't use that one at all for this. Total distance traveled. Now, I'd be very comfortable giving you this without a calculator, first of all. The graph, let's say we're just going from 0 on. From 0 to 5 is what we're looking at. 0, if I plug 0 in, we're down here at -9, and then we have an x-intercept at 3. So here would be 3, and then let's say we keep going to 5. This is negative area, and that's positive area. And the area under the velocity is how far we've traveled. It's the displacement, right? So if we want the total, individually it's the displacement. We have negative displacement, we have positive displacement. When you add those together, you get the overall displacement. But we want these to count as positive if we're going to get total distance traveled. We need the absolute value integral from 0 to 3 of v of t plus the absolute value from 3 to 5 of v of t dt. Now, if you don't know what the graph looks like, you have to at least be able to get the zeros. So you're going to split that over the zeros and make sure all of the area is counted as positive. So this right here is total distance traveled. If you can use a calculator, splitting over zeros would be a huge waste of time because now you could go 0 to 5 of the absolute value of v of t dt. Because now what absolute value does is it takes all of these negative values and makes them positive. So the absolute value graph would look like this. So now that negative area becomes positive, that positive area stays positive. So that's what you do if you had a calculator. All right, but evaluating this, first of all, would answer this question. We're done. Other than evaluating it, we're done. However, I want to move on. I want to keep going with this. What would this be? And I've kind of already said it. Yeah, that's the overall displacement. If I did this, what would this be? That'd be the final position, right? That would be the final position because we're starting at 6 and adding the displacement gives final position. This is a nice little summary of at least those vocabulary words. Talking about total distance, talking about what is just displacement all by itself, and then what do you do to that to get final position. So we went way beyond answering that question. We good? Just thought it'd help. Just throw it on my desk when you're done. Oh, I like this question. Talk to your partner about this one. This is one of my. It's not that hard. It's a kind of a neat little twist to it. Okay, we got quiet. What is it? Yeah, it's sine, isn't it? It's sine. Because this is, if this represents the length of the curve, this is the derivative squared. So this must be the derivative. And the derivative of sine is cosine. So y equals sine is what we're measuring. We're measuring the arc length of sine from 2 to 5. That'd be the formula. It's kind of a nice little twist on that formula. Questions on how we develop that? All right, that kind of takes care of chapter 7. And I usually try to review the other questions that may or may not be on the test. They're on the test. Okay, so let's try these. Implicit, find dy dx. So we take the derivative of 3, that's 0. Derivative of sine is cosine, but then the derivative of the outside is 2, but we're taking the derivative with respect to x, not y. So we write dy dx. That's 1 plus 2, but we just took the derivative of y again, so dy dx. Oh, let's go cosine of 2y. How about we put the 2 out front here? Dy dx minus 2 dy dx equals 1. Factor out the dy dx and divide. So 1 over 2 cosine of 2y minus 2. Then we could ask, like, evaluate the derivative. Where's the derivative? Undefined. We'd set the bottom equal to 0, and there's all kinds of questions that can go along with this. I had, on your paper still, this says g prime, which would be wrong. That wouldn't be g prime. The question would be, if g of x equals this, what would be g of pi over 3, not g prime of pi over 3. G prime kind of gives you a hint as to what happens here, but that would not be correct. What is this? Yeah, formal definition of derivative. And so the derivative of sine is cosine. So g of x is equal to cosine of x, because that's the formal definition of derivative. So over here, we're looking for the cosine of pi over 3, which is 1/2. So you can imagine if this was a multiple choice, A might be 1/2. Guess what B probably is as a distractor? Square root of 3 over 2. Because you're just going to look at this and go, oh, sine of pi over 3, square root of 3 over 2. I'll bet B is square root of 3 over 2. Now, I don't know what C and D would be. Maybe 0 and 1. Who knows? But anyway, the answer is A, because you have to take the derivative. A common mistake is just leaving it as sine, not taking the derivative. But why would a calculus question not have derivative in it, right? If you're not taking the integral of derivative, you're probably doing it wrong, right, by this point? Okay. Try that one. This one is not a mistake. F of x is that. What would f prime of x be? feel free to talk about it. There we go. There's the answer. If you would do the integral, you would plug in to whatever the integral would be. You'd have something, and you'd plug in x to the third, minus something, and you'd plug 5 in. But then you would take the derivative, and this would be the inside of the something. But then you'd take the derivative, you'd get right back to this with this now on the inside. So the derivative, this you'd have to multiply times the derivative of the inside. That's where this comes from. The reason there's nothing on the end of this, because this was just a value. It would have just 5 plugged in. It wouldn't have any variables anymore. And what's the derivative of a constant? 0. So it'd go away when you took the derivative. So there's your answer over there. I stand corrected. This problem, we're not taking the derivative of anything. Find the midpoint Riemann sum with 3 subintervals. Use a calculator. This is kind of the foundation of derivative, though. So there's 1 subinterval, 2 subintervals, 3 subintervals right there. Now we're using the midpoint to find the height of the rectangles. So from 2 to 7, we have a base of 5, but we're using the 3 to get the height. So times 23. It's a midpoint Riemann sum. So 7 to 13 is 6, but we're using the midpoint to find the height. And finally, the last one, 13 to 18 is 5, but we're using the midpoint to find the height. And I said use a calculator, but it turns out this one's not that bad. 120 plus 65. So we're actually adding 185 to this, and I think that turns out to be 300. So 300 is the answer. Yeah, go ahead. Three is in the middle of the values we have. What are you suggesting we use? What would we use other than 3? Right, it's not halfway between 2 and 7, but that would be called, and I'm not being sarcastic, it's not called the halfway point sum. It's called the, I know what you're saying, like, wait, midpoint is halfway. Done. But we're using midpoint as the middle value, somewhere in the middle. Does that clear it up a little bit? Okay, so if we went 3 subintervals and we're using a point in the middle, think of that as the middle point, not necessarily the halfway point. Okay, yeah. Anything else? All right. That's what we got.